Okay, here's quite an interesting example of a modulus equation. Let's see how far we can get without the sketch graph, but I think we're going to need some graphs at some point. So the first thing we can say is that I've got a modulus. Now that modulus could have no effect. So it could be that the modulus of x squared minus 1 is just x squared minus 1. And it could be that the modulus of x is just x. So this is one possible equation that might generate some solutions. But there are other possibilities. For example, moduluses can do a sign swap. So it could be the modulus of x squared minus 1 is minus the modulus of x squared plus 1, because the modulus swaps the sign of the entirety of what's inside it. And it could be that the other side, the modulus, has an effect. In other words, that is actually not an x, it's a minus x. But this has always got to be a plus 1. And these two equations will have different solutions. And it could be that the first modulus does have no effect, so that's x squared minus 1 still, but this one does, so that equals x plus 1. And it could be that the first modulus is the one that has an effect, so that becomes x squared plus 1, and on the other side I've got no effect from the modulus, so I've got that. These four different equations are all potential solutions to this. So these are all quadratic equations. Some are easier than others. Okay, in a couple of them I've got a plus 1 on each side which cancels, so they may be the easiest ones to start with. This one I'm going to get, if I get naught on this side, so the ones have cancelled, I'm adding x squared to both sides, so naught equals x squared minus x, which factorises as x brackets x minus 1 equals naught. Okay, so I'm going to be able to solve that. This other one, this is quite easy. Here I've got very similar. The ones cancel. I can add the minus x squared to both sides. So naught equals x squared plus x, which implies that x brackets x plus 1 equals naught. So let's label these. This is A, B, C, D. So I've dealt with B and I've dealt with D. Now A is a more normal quadratic equation, x squared, I'll take away this x and this one from both sides, so x squared minus x minus 2 equals naught, which we can factorise. So for A we would say that x is going to have to be minus 2 and x plus 1 equals naught, and for C this becomes the quadratic x squared plus x, and it's going to be minus 2 equals naught, and C factorises as x plus 2, x minus 1 equals naught, and B factorised as x minus 1 equals naught, and D factorised as x plus 1 equals naught. And putting all the solutions together, I can see the x values that make A work are 2 and minus 1, and then from B the x values that work are naught and plus 1, and then from C I've got minus 2, and I've got this solution, I've had it before but I'll write it again, this is solution 1, and from D x could equal naught or x could equal minus 1. So I'm getting some solutions more than once. Now some of these are valid solutions, others aren't. Okay, now I suppose I could actually just test each one in turn in the equation and find that some work and some don't, but let's see why some work and some don't. Okay, and this is something you could have started with by sketching the two graphs. Okay, so for the graph of modulus of x squared minus 1, well, without the modulus, y equals x squared minus 1, its graph would be, well, it's an x squared graph, but the minus 1 outside means it's translated down 1 unit. So that's 1, and these roots here, when x squared minus 1 is naught, this is actually minus 1 and this is 1, and of course you can do some of these graphs on a graphical calculator, but I'm doing them by hand. And remember, the effect of the modulus is to take this negative set of values here and turn them into positives. So my x squared minus 1 graph, modulus of that is one of these parabolas which have the bottom of the bump reflected upwards. And then on the other side, modulus of x plus 1 is the modulus of x graph just bumped up by 1, because there's a plus 1 translation. Okay, or you could use the point of the v method. The point of the v is going to be when the contents of the modulus are 0, which is when x is 0, and then y is going to be equal 1. So it's a v with its point at 0, 1. So if I put those two graphs together, the one I've just been talking about, okay, the modulus one, this is the modulus graph with the point of the v at 0, 1. and then the parabola, okay, comes down to -1 here and 1 here. Okay, and this value of -1 when reflected upward becomes a +1. So this bump of the parabola is actually going to just touch the modulus graph there. And then the other bits of the parabola, the non-reflected bits, sorry, I mustn't go back on myself, okay, will look something like that. Okay, never let your graph curve back. It's always got a downward slope here. So the actual solutions are, I've got one here. Now that's clearly 0. So I got the solution 0, I actually got it twice. And then the other solutions are here and here, which are clearly not -1 or 1. So the other solutions that are valid are 2 and -2. And then so if I look at all the solutions I got, there are only 3 valid ones. This 0's a repeat of one of the valid solutions. But then the other 2 solutions that have come up a couple of times each are 1 and -1. Now why have the equations given me that solution? Well, when I do these possible equations, okay, I've just said these are the things that the modulus could do, but not when it does it. So in other words, -x plus 1, okay, which is this downward sloping part of the graph. This is a graph of y equals -x plus 1. Okay, that equation is only valid, actually, I can now see for negative x's. If I'd carried that equation onwards, then lo and behold, I would have got an extra solution there at 1. I haven't drawn it very well, but the gradient of that is -1, and the gradient of this is -1. So I would have got the graphs agreeing at 1. It doesn't happen, because that equation, y equals -x plus 1, which is perfectly valid for this bit of the modulus graph, it stops being valid at the y-axis, and so this bit of the graph, this dotted part, doesn't exist, and this isn't a solution. And similarly for the solution at -1, that would be this part of the graph coming back. We call these spurious solutions. You don't need to know that word, but that's what they're called. So the actual values for x, now I've drawn the graph, I can see the actual values of x are -2, this one here, and 0, the one I can see from the graph in the middle, and 2, which is this one here. So those are my answers, and I hope that helps.